In this video, we're going to have a look at this topology here, which on the surface looks fairly innocent, but actually it contains quite a lot of components in Azure that behind the scenes are quite interesting to network engineers. There's lots of BGP happening here. And if you know where to look in the portal, in the CLI, you can build out the understanding of the topology, which will help bolster your understanding of how the routing's working. This is all based on one of my colleagues, Daniel Mauser's GitHub repository. So I'm sure you know Daniel. If not, check out his work. He documents these lab topologies, and this one is quite old now from when Route Server first came out, but it still works perfectly, which I guess is a testament to the backwards compatibility of the Azure API, etc. And you can see in this diagram here that the whole idea is that you've got an Azure Hub Virtual Network and you've got VNets hanging off it. And on the bottom, you have a branch or an on-site, an on-premises site that's connected via VPN. So that VPN can access stuff in Azure. But then you also have an ExpressRoute connected location. Could be another on-prem location, but there are quite a lot of scenarios in Azure where technologies are used inside of Azure to go from an ExpressRoute gateway to an internal circuit for things like Azure VMware Solutions and SkyTap on Azure. So if you're a customer who's trying to connect over VPN to Azure and then you need to get access to AVS, this is a topology you might run into. And there are a few requirements that you need to be aware of, such as when you deploy the route server, this bit in the middle here, this VPN gateway needs to be in an active-active configuration. And that may bring into question, well, do I need tunnels from on-prem? Do I need to use BGP, etc., etc.? Well, in my lab, I changed this default rollout that Daniel's built here. And rather than having two tunnels from on-prem connecting to both active instances of the VPN gateway, I've reduced that down to one tunnel. And in my lab, I'm not using BGP because some customers are not using BGP. And the question may be, well, can I still make this work? And as Daniel points out elsewhere in his guide, you don't have to run BGP between the VPN gateway and on-prem to get this transit scenario working. Furthermore, what I'll show is you don't need to have two active tunnels to your Azure VPN gateway. There are reasons why you might want to, but if you just build one tunnel, this will still work. The thing that is doing most of the work here is the Azure Route Server. So these gateways, normally they don't exchange routing information. You normally can't come into Azure and then leave Azure from two different branches. But the route server, there's a toggle on it called Branch-to-branch. And this effectively enables this flow. And as we'll talk about in more detail, this is happening because each of these gateways is building an iBGP session to the route server, which is acting as a route reflector and allowing them to exchange routes, which are then propagated to their associated branches. So then the branch thinks that it can go to Azure for the other branch. So VPN, for example, thinks I can get to Azure and go down to ExpressRoute, and ExpressRoute thinks I'll go to Azure for what is a VPN branch prefix. So that's the high level idea, but the focus of the video is going to be more on building out in our brains that transit topology based on BGP, looking at some of the routing information, showing us where that's available in the portal, and then adding to our diagram with some of the next hops, etc. So let me flip over now to a split screen, and we'll have the portal and the capturing the information on one side. And then on the right hand side, we'll build out a diagram with more detailed information. All right, so here we have on the left, we've got our Azure portal, we've got access to the Azure Cloud Shell, so we can run some commands, etc. And on the right-hand side, we've got what at first might look like a scary diagram with lots of IP addresses on there, next hops and different colors, etc. but that's where we're going to build it out to understand where these IP addresses come from and why they're important if you're troubleshooting this, etc. So we kind of got red for the ExpressRoute portion of our topology. We got grey for kind of the bits in Azure, purple for the route server, and then we got blue for the bits associated to VPN. And actually my on-premises branch here, as in Daniel's lab build out, this on-prem location I'm just simulating in Azure. This is just another VNet isolated with a VPN gateway. And I'll show you how it's configured to reflect what we said earlier about single tunnel, no BGP. So let's go from left to right, and we'll take our time with this. And we'll go blue, and then we'll go purple and red. So let's start off with on-prem and show you what that looks like in Azure. So here we have my on-prem, let's imagine this to be the firewall, the on-prem firewall that's terminating your IPsec connection. As I said, in my case, it's an on-prem simulated gateway. It's a virtual network gateway in Azure. And actually, if you're particularly keen-eyed, you'll see my resource group is actually named after Daniel, so DMauser. So thanks again to Daniel for the fast lab build out here. So we've got route-based VPN, VPN Gateway 1 SKU. You see it's got a public IP there. It's running in active standby mode, which means effectively there's only one active node under the covers. I haven't enabled active mode on my on-prem side. In Azure I have, because that's a prereq to use Azure Route Server, and you'll understand why later. Configure BGP is turned on, but we're not actually using BGP, and we can see that if we look in the connection. So here we have one single connection that's going from my on-prem gateway to a single instance of the two available instances I have of the Azure VPN Gateway, two instances as part of the one Azure VPN Gateway resource. Of course, we can't deploy multiple Azure VPN gateways in one gateway subnet. And if we look at the connection properties here, we can see that the connection itself is not using BGP. Everything else is default. And then the way in which Azure deals with the settings for the remote end is we associate a local network gateway. That's the resource that contains the settings for the remote end. It's sometimes a little bit hard to wrap our heads around how that's how the nomenclature works. So you see here the local network gateway for 4.223.140.68, which is the PIP associated with my VPN gateway in Azure. We can look at the settings for that. The bit we're interested in is no BGP. We're statically specifying the remote end. And what have we said? Here we said on the remote end, there is the address space 10.0.1.0/24, which is associated to a spoke that's hanging off my hub. So I actually need to update my diagram there to include that VNet that's hanging off the hub. Now this configuration doesn't make a lot of sense for a production environment because you haven't actually got access to the hub address space here. So, you know, really I should go in here and add 10.0/24 like this. But this demo and this explanation is more about connecting from VPN into Azure and then going back to my ExpressRoute connection, not really about getting into Azure itself. So I'm not too worried about that there. This is the one which is important. It's saying effectively to the on-prem network that come to me for anything in this 192.168.2.0/23 range. I can use /23, I could use /16, I could use whatever I like, as long as it's, you know, bigger than this space, which is a /24. It would work with a /24 as well. I was just playing around in my testing to make sure it functioned fine with SuperNets, and it does. Okay, so that's the on-prem side, relatively easy to understand. Static routing to the VPN, single tunnel into Azure. So now we can have a look at the other end of it, shall we say. This is the blue VPN gateway in Azure. You can see the config looks kind of the same, but an important distinction is we have enabled the active-active mode. BGP is enabled on the VPN gateway, but that is not being used on our VPN connection there. It's not a requirement. And you can see because it's an active-active VPN gateway, there's two instances. So there's one public IP, two public IPs, and then there's two internal BGP addresses. So we can put that information on a diagram. I've put the two PIPs there. I've only put the IP address of the PIP we're using. This other one over here, this PIP, is sort of sat there, nothing's attaching to it. And then we've got those two internal BGP addresses, 10.00.44, 10.00.45, and they are coming from our gateway subnet. And we've got that connection there and the associated LNG, etc., going back to on-prem. Just for completeness, I'll show you that. The LNG this time, the logic is reversed. It's saying this is the PIP on-prem, and the address space is reflective of what's on-prem, which is 192.168.100.0/24. In our hub virtual network, if we go to subnets, I can show you that, that gateway subnet there. So the gateway subnet is using IP addresses from 0032 up to 00.63, and you can see all of these IPs in my diagram are from that range. So when you look at the guidelines for deploying gateway subnets, you know that you've got certain guidelines on it needs to be a certain size. And sometimes you start thinking, well, why does it need so many IPs? And topologies like this start to give you an idea why, because IP addresses from the gateway subnet get associated to a lot of places, and some places where you wouldn't expect, as we'll see with ExpressRoute. So I've showed you where these IP addresses come from, the blue IPs. We can look at Azure Route Server. So Azure Route Server gets deployed in its own subnet called Route Server Subnet. If we look in connected devices on the virtual network, you actually see the two instances of the route server, 0 and 1, and those are the IPs there. Behind the scenes, what's happening is the route server is peering with the VPN gateway via iBGP. They're both in AS 65515. So the actual control plane traffic is, as I said before, it's acting as a route reflector. And there is a place actually in the VPN gateway where we can start to get some of that detail in the portal. There's a BGP peers section here. So remember, I'm not using BGP to any external networks from that blue VPN gateway in Azure, but we will see some BGP peers here. And actually this is interesting, right? You see the BGP peers to the route server, right? So we've not revealed any platform underlying information here. We're just working this out as we go along. Those are the peerings to the route server. And you can also see that the gateways themselves are connected by iBGP. So there's connections there. And we can also see some of the learned routes, but I'll leave that for a little bit. We'll look at that. We'll look at that shortly. Okay, this is where we need to start looking at some of the routing to start adding a bit more detail to our diagram. And this is just a CLI print of what you kind of saw in the portal earlier with the VPN gateway. So I'm listing the learned routes for the VPN gateway here. And you see you've got a double print output here because there's two instances, but let's just look at one half of it. And let's see what, just take them one by one effectively. So the first one, the first three actually kind of make sense, right? You've got, these are all VNet address spaces. So they're sort of the Azure networks, and the source peer is sort of itself. That's kind of Azure's way on the VPN gateway of saying they're just on net. We haven't got to worry about them. The interesting ones though are here. So this one here, this is our ExpressRoute branch effectively. You see 192.168.2.0. And you see, where am I getting the information from? It's coming from 132.133. That's the route server. Okay, makes sense. Next hop, 0.36. That's interesting. We need to sort of work out where that is. AS path looks like this. So you've got kind of the Microsoft Edge 12.0.7.6, and then the rest of it, that's what my on-prem branch is set in when they're advertised to Azure. The next one of interest here is the 192.168.100.0. So this is my on-prem VPN branch, and we can see that the next hop is .44, which is the BGP address associated with the active instance that's getting those routes from on-prem. And we're learning that from a few different places. We're learning it back from the route server. We're learning it from our iBGP VPN Gateway peer. But ultimately, all of those rows lead to the same place, which is, from a node perspective, you go here or you go here. And even the route server knows that ultimately you have to go here to get back to the branch on-prem. But it's really the ExpressRoute bit where we want to zoom in on and start unpicking the rest of the diagram here. Okay, to add a couple more IP addresses to our picture, I've run this command here on the ExpressRoute circuit itself. So on my diagram, I've got a circuit here, and I've got on-prem here, and the circuit is connected to on-prem via BGP. So with this command is dumping the circuit and peering information from this area here. So first of all, I'm just having a look at, show me what neighbors you've got. And we see we've got an on-prem neighbor, 169.254.1.1. I've just noticed a mistake in this diagram. That should be AS 65,000 as the direct neighbor. But the bits that are really interesting is here. AS 65.515, which we know is our gateway in Azure. And these are the IPs, look, 46 and 47. So these are IP addresses from our gateway subnet that are associated with the ExpressRoute gateways. Okay, so we add that information to our diagram. So you see now we've got 2 IP addresses on the gateway for ExpressRoute, 2 IP addresses on the VPN gateway. But remember earlier, the next hop address from the VPN gateway's perspective for ExpressRoute wasn't .46 and .47, it was .36. Why is that? And what is that? It's still coming from our gateway subnet, right? It's still from that range, but where is it? Well, the short answer would be, as we know from other videos, when traffic leaves Azure to ExpressRoute, the gateways are bypassed in the egress direction. The inbound traffic goes through the gateways, unless you're using FastPath, but in the egress direction, it goes direct to the Microsoft Edge. How can we verify that even further? Well, we can run a similar command, this list learned routes command. Notice now I'm running it on the ExpressRoute gateway. So let's go down the list now. We've got 10.0.0, which is my VNet, next hop 46, which is kind of itself. Okay, that makes sense. Now we've got the on-prem VPN branch via .44, which is that address associated with the active VPN gateway instance, which has got the tunnel pinned to it. That now makes sense. Learn from the route server. That makes sense. What about the on-prem ExpressRoute branch from the perspective of the gateway? Remember, the gateway and the circuit are very distinct objects. Well, the gateway knows about it from these IP addresses, 36 and 37. What could they be? Well, these are actually IP addresses associated with the circuit devices. So down in the edge location, they actually get an IP address from your gateway subnet. So there's IP addresses here, and there's BGP sessions formed between them. eBGP session, as you can see here, because it's 65.515 for the gateway, but 12.0.7.6 for the edge network. And you can see these routes are learned from multiple places. So putting this all together, we can sort of see how the end-to-end traffic flow works here. The on-prem VPN branch knows statically to route to Azure traffic across the tunnel due to the LNG config for this prefix. Okay. Traffic gets to this instance of the VPN gateway, and as per its routing table, for the ExpressRoute branch, we will send it to the edge, which then goes to on-prem. Then the reverse packet has to come back. This network needs to reply to the original source, which was down here. How does it know how to send a packet to 192.168.100.4? Well, on-prem knows about the routes advertised via ExpressRoute. If we look at the routing table for this circuit, the things that it is advertising in this direction, we can look here at the circuit. It knows about this range. It knows about 192.168.100.0 from these IPs, which we know are the gateways now for ExpressRoute. So the ExpressRoute gateways have been influenced by the route server branch to branch to advertise onwards the VPN prefixes. It comes into the circuit routes it as per this logic. So as we said, without fastpath, traffic comes in through these nodes in the gateway. What does the gateway do with the traffic? Well, we have our answer from the route tables before. The ExpressRoute route table says, how do I get a packet to 100.4? Well, it looks here. Okay, my next hop, put it on the wire destined for .44. It puts it on the wire destined here. And then the VPN gateway routes it as per its routing table, which is all of this information here, which we know is generated from the LNG config, statically routed down that single tunnel back to on-prem. Maybe one final thing we can do here, just to sort of land home why the behavior's changed here with route server. If I go into my route server config in the portal here, go to configuration, let me disable branch to branch, and I will save that config. And we'll have a look at the impact on our route tables, and you'll see how it changes. Okay, so I didn't subject you to the time you need to wait for the route server to save its setting, but yeah, the diagram now reflects branch to branch disabled. Here I'm looking at the ExpressRoute routing table again. Notice now we're missing the VPN branch, no 192.168.100.0. That's gone. So we've broken our transit via Azure, which route server was facilitating. And if we look at our outputs again from our gateways, they're similarly affected. So if we look at the VPN gateway, it has no idea that 192.168.2.0 exists. It would have no idea how to route that traffic. It would get it, and it would effectively black hole it, even if our VPN gateway was statically routing that traffic. And in fact, there would be issues with the traffic selectors with IPsec set up anyway. Again, on the ExpressRoute gateway, we've got a similar problem, right? If you sent traffic this way, I mean, it wouldn't get past the edge network for a start. Even if the gateway got that traffic destined for 100.4, it has no idea how to get there. There's no route for it. It doesn't know to send it to the VPN gateway. That's because there's no iBGP to the route server anymore. There's no route reflection happening. So that's the unlock that's happened here with the route server. So nothing particularly new in this video, just demonstrating a feature of the route server and going under the covers a bit, showing you that if you know where to look in the portal and CLI commands, you can start to build out these topologies. And I found that some of these exercises can make things click for network engineers who very much want to know the path of traffic, etc. So thanks for watching again.